This lecture is lecture 29, covering 9.5 to 9.6 and 9.9. So let's introduce the idea of partial pressures. So Dalton's law of partial pressure states that the total pressure exerted by a mixture of gases in the container at constant volume and temperature is equal to the sum of the individual gases' pressure in the container. So we can see here that our total pressure, sorry, my mouse get over here. So my total pressure in a single vessel is equal to the summation of all of the individual pressures of all of the individual gases within that container. Okay, so if you have 3 or 4 different types of gas, so say oxygen gas, CO2 gas, nitrogen gas, each of those individual gases has a certain number of moles associated with them. And using PV equals nRT, we can indicate the individual pressure associated with the amount of gas of each of our different types of gases. So the total pressure within a single vessel will be equal to the summation of those individual pressures of all of our individual gases. So this Dalton's law of partial pressures equation that's given to us here, P total is equal to P1 plus P2 all the way up to summation to P sub n, makes for a really straightforward and easy problem for us to be able to work through. So let's consider 2 different examples here. So example 1. Consider a steel vessel that contains a mixture of oxygen, argon, and nitrogen gases at 25 degrees Celsius. What is the total pressure in the vessel if the pressures of oxygen, argon, and nitrogen are 0.25 atmospheres, 0.50 atmospheres, and 0.15 atmospheres, respectively? So Dalton's law of partial pressure states that our pressure total is going to be equal to the pressure of our individual gases. So in this case, we have pressure of oxygen gas plus the pressure of our argon gas plus the pressure of our N2 nitrogen gas. So we can just simply input all of our individual values. And so the units for these individual pressures don't matter as long as the units are the same. So we can put in our pressure for oxygen, which is 0.25 atmospheres, plus our pressure for our argon, which is 0.50 atmospheres, plus our pressure for our nitrogen gas, which is 0.15 atmospheres. So if we plug and chug here, we can find that our total pressure in that vessel is equal to 0.90 atmospheres total. Okay, so to visualize this, we have a single vessel that has O2 gas, argon gas, and nitrogen gas. The volume of this vessel is fixed because it is a steel vessel, so that volume remains the same. And it's held at constant temperature, so the temperature remains the same as well. Okay, so the total pressure inside of this vessel is indicated by the summation of all of the pressures of our individual gases. Okay, let's work through the next example here. So the next example states, consider a balloon with a mixture of hydrogen gas, oxygen gas, and carbon dioxide gas. The total pressure inside the balloon is 100 kilopascals. The partial pressure of the hydrogen gas and oxygen gas are 23 kilopascals and 50 kilopascals, respectively. What is the partial pressure of carbon dioxide inside of that vessel? Okay, so for this, we're going to use that same Dalton's law of partial pressures, where we see that the pressure total will be equal to the pressure of our hydrogen gas, the pressure of our O2 gas, and the pressure of our CO2 gas. So here we're trying to solve for what is the pressure of the CO2 gas. So we can rearrange this equation to solve for the pressure of CO2. So the pressure of CO2 would be equal to the total pressure inside the balloon minus the pressure of H2 gas minus the pressure of O2 gas. So this is a simple plug and chug equation. And as I stated previously, that it doesn't matter what the unit is for each of these individual pressures, just that the unit stays the same. So even though this problem is in kilopascals, whereas the last problem was in atmospheres, that's totally fine. So our total pressure we were given as 100 kilopascals minus our pressure of hydrogen, which is 23 kilopascals, minus our pressure of oxygen, which is 50 kilopascals. So we can then plug and chug, solve for our pressure of CO2 is equal to 27 kilopascals within the balloon. Okay, so that's the Dalton's law of partial pressures, which is a pretty straightforward equation. So let's think a little bit more deeply into this Dalton's law of partial pressures. So since we know that the ideal gas law states that since PV equals nRT and volume and temperature are fixed in this individual vessel because it's all in one vessel, Dalton's law can be rewritten as the pressure total is equal to the summation of all of the moles of gas times RT over V. Again, where R is our gas constant, T is our temperature in Kelvin, and V is our volume in liters. Okay, so let's think about this for a second to make sure that this makes sense. So if we know that PV equals nRT, if we rearrange this equation and solve for P, so P is equal to nRT over V. So if we know that P total is equal to pressure of, say we have a mixture of O2 gas plus CO2 gas plus N2 gas, we can rewrite this equation using the ideal gas law for each of these individual components here. So the pressure total would be equal to the number of moles of O2 times our gas constant R times our temperature over the volume of the vessel, plus the number of moles for CO2 times RT over V, plus the number of moles of N2 gas times RT over V. So we can notice here that this RT over V term is present in each of our individual terms. Because of that, we can pull that out to simplify the equation to say that the total pressure in the vessel is equal to the summation of the number of moles of O2 plus number of moles of CO2 plus number of moles of N2 times RT over V. Okay, so this shows that we can rearrange this Dalton laws of partial pressure to indicate a summation of the number of moles, if that's the information that we're given. Okay, so when we're actually looking in real life examples, the composition of gases in a mixture are typically represented as a mole fraction. And so the mole fraction, which is given to us by the Greek symbol chi sub I, which the chi looks just like an X. So the mole fraction chi sub I is equal to the moles of the component or moles of an individual gas over the total number of moles in the mixture. Okay, so the number of moles of the individual gas over the total number of moles. Okay, so we can rearrange this equation to get the mole fraction of a specific gas is equal to either the number of moles of the gas over moles total, or rearrange to say the partial pressure of an individual gas over the pressure total. Okay, so this take-home message here is that our partial pressure for an individual gas has two different definitions. One is the number of moles of an individual gas over number of moles total, or the partial pressure of an individual gas over the total pressure within the system. So let's prove to ourselves here that this dual definition of our mole fraction, so again, this chi sub I is our mole fraction. Okay, so this definition here makes sense. The number of moles makes sense. Let's prove to ourselves that we can actually express this mole fraction in terms of partial pressures. So again, knowing that PV equals to nRT, if we rearrange for N, okay, so rearrange the law of partial pressure, or sorry, excuse me, our ideal gas law to solve for N, we see that N is equal to PV over RT. Okay, so if we substitute this N sub I for the PV equals RT, We can see that chi is equal to our pressure of our individual gas times volume over RT over the partial pressure or the pressure total times the volume over RT. So we can see that we have volume over RT on the top and volume over RT on the bottom. So these two terms are going to cancel each other out, leaving us that the mole fraction is equal to the partial pressure of our individual gas over the total pressure. So this proves to ourselves the secondary definition of our mole fraction. Okay, so furthermore, once we have this definition of mole fraction, having two different ways to solve, either our ratio of our partial individual moles over the total moles or the individual pressure over the total pressure, we can rearrange that equation to state either that the partial pressure of an individual gas is equal to our mole fraction of the specific gas times the pressure total, or we can rearrange in terms of our N, where our individual number of moles is equal to our mole fraction times the total number of moles of gas within a solution. Okay, so these are simply a rearranged form of these equations above. So let's take a look at a problem that uses this mole fraction equation. So a 10-liter flask containing 2 moles of argon, 3 moles of neon, and an unknown amount of helium has a total pressure of 24.5 atmospheres at 25 degrees C. How many moles of helium are in the flask? Okay, so here we're going to use our Dalton's law of partial pressures definition, that the pressure total is equal to the summation of our number of moles. So in this case, we're going to have moles of our argon plus moles of neon plus our moles of helium times RT over V. Okay? And so we know that PV over RT is going to be equal to our total number of the summation of all of our individual moles of gas. So our number of moles of gas total. And so given our total pressure and our temperature, we can then solve the problem here for our N total. So we know that our pressure is 24.5 atmospheres. We know our volume is 10.0 liters. We know our gas constant is 0.082058 atm liters over mole Kelvin. And our temperature, 25 degrees turned into Kelvin, we know is 298.15. Okay, so we can solve here and say that our number of moles total is going to be equal to 10.01 moles. Okay, so now we can determine what our total, so if now we know our total number of moles here, we can rearrange to solve for the number of moles of helium that we don't know. So we know that our number of moles total is equal to our number of moles of argon plus number of moles of neon plus our number of moles of helium. We can rearrange to solve for number of moles of helium. Number of moles of helium is equal to our number of moles total minus our number of moles of argon minus our number of moles of neon. So we can plug and chug here and say that 10.01 moles minus 2 moles, 2.00 moles of argon minus 3.00 moles of our neon will give us our final answer of 5.00 moles of helium. Okay? So this is a problem using our idea of Dalton's law of partial pressure to solve for an unknown amount of moles of gas. Next, a balloon contains 0.76 moles of N2 gas, 0.18 moles of O2 gas, 0.31 moles of helium gas, and 0.026 moles of H2 gas at 739 millimeters of mercury. What is the partial pressure of O2? Okay, so for this problem, we're going to be using our partial pressure equation that states that the partial pressure of an individual gas is going to be equal to our mole fraction of that individual gas times our total pressure. All right, so here we can see that the mole fraction for our, so here we're talking about O2. So this equation here, we can change that to talk about the partial pressure of O2 is equal to the mole fraction of O2 times our total pressure. So if we want to solve for the partial pressure of O2, we can see in our problem that we have, so that's going to be our number of moles of O2 over a number of moles total. And so our number of moles of O2 given to us is 0.18 moles of O2 over our total number of moles, which is going to be the summation of all of our moles together. So N total will be equal to our number of moles of N2 plus the number of moles of O2 plus the number of moles of helium plus the number of moles of H2. So we can plug all these in. So number of moles of N2 is going to be 0.76 moles plus the number of moles of O2, 0.18 moles, plus our number of moles of helium, which is 0.031 moles, plus our number of moles of O2, which is 0.026 moles. Plug and chug, we get our number of moles total is going to be equal to 0.997 moles total. So we can take that value, plug it into our equation up here. 0.997 moles total. Okay, plug and chug from here, we get a mole fraction for O2. So I'm going to erase down here so we have a little more room to operate. Our mole fraction of O2 is going to be equal to 0.1805. All right, so now we have this value of the partial pressure of O2 up here. And in the problem, we're giving our total pressure for the system 739 millimeters of mercury. There's no need to change our units here because we're just determining the partial pressure of O2. It doesn't state the number of units in the problem. So we can simply just plug in the values we have. So our pressure of O2 is equal to our mole fraction, which is 0.1805, times our total pressure, which is 739 millimeters of mercury. And that gives us a partial pressure of O2 equal to 133 millimeters of mercury. Okay, so that gives us our answer C on our list. Okay, so that's cut down to 2 sig figs, 130. Okay, on a humid day in the summer, the mole fraction of gaseous water vapor in the air at 25 degrees Celsius can be as high as 0.0287. Assuming a total pressure of 0.977 atmospheres, what is the partial pressure of water in the air in atmospheres? Okay, so we're going to again use our partial pressures equation here using our mole fraction, where our partial pressure of our gaseous water is going to be equal to our mole fraction of our gaseous water times the total pressure. So if we're solving for our partial pressure of that water, we have all the information needed, and we can simply just plug and chug. Okay, so our pressure of our water is equal to our mole fraction, which is 0.0287, times our total pressure, which is 0.977 atmospheres. And that gives us our final answer equal to 0.0280 atmospheres partial pressure for water. Okay, so you can see it's a pretty straightforward process using mole fraction to convert between our total pressure and partial pressure of an individual gas. Next, at an underwater depth of 250 feet, the pressure is 8.38 atmospheres. What should the mole percentage of oxygen in diving gas be for the partial pressure of oxygen in the gas to be 0.21 atmospheres, the same as in air at 1.0 atmospheres? Okay, so for this, we're going to be taking a look at, we're going to again be using our mole fraction partial pressures equation. So we're going to talk about the partial pressure of oxygen is equal to the mole fraction of oxygen times the total pressure. Okay, and so in this case, we have to solve for our partial pressure of O2. So we know that partial pressure of O2 has two different definitions, our number of moles of O2 over number of moles total, or our partial pressure of O2 over our pressure total. So in this case, we have the information for the partial pressures in order to solve for our mole fraction. So we can say that we're looking for a partial pressure of 0.21 atmospheres over a total pressure of 8.38 atmospheres. And that solves for the the mole fraction of O2 as equal to 0.025, which if we convert this to percentage by multiplying by 100 would give us 2.5% O2. Okay. Next, a mixture of two gases, A and B, have a mole fraction of A equaling 0.48. If the volume of the vessel is increased by 2 and the Kelvin temperature is decreased to 1/2 of the initial temperature, what is the mole fraction of A? Okay, so I want you all to take a moment to think about this question. Pause your video, think about it, and then unpause, and then we'll discuss. Okay, so we're talking about the mole fraction. So the mole fraction, we know the mole fraction of an individual compound is either equal to our number of moles of that compound over number of moles total, or the partial pressure of an individual compound over the partial pressure P total. So is there anything in this equation that has anything to do with our temperature or our volume? No, there's nothing in this equation that has to do with volume or temperature. So you can change the volume, you can change the temperature at all. It doesn't change the number of moles of gas in that specific container. So the correct answer here would be C, 0.48. So the mole fraction is unchanged by changing temperature and changing volume. Okay, so next we're going to shift gears a little bit to discuss the kinetic molecular theory of gases. So this is a theory that includes 5 postulates that sort of explains the entire nature of gas behavior as we know it. So the first postulate is 1, a gas consists of tiny particles, either atoms or molecules, that move about at random. 2, the volume of the particles themselves are negligible compared to the total volume of gas. Most of the volume of gas is empty space. So we know this is true because you can compress gases. Three, the gas particles act independently of one another. There's no attractive or repulsive forces between the particles. So those individual gas molecules are flying around at random within this container that's mostly empty space, and they're not being attracted or repelled from each other. They're just moving around by themselves. Four, collisions of the gas particles, either with other particles or with the walls of the container, are elastic when at constant temperature. So elastic collisions mean that there's no energy transfer, either energy gain or energy loss associated with those collisions. All right, so the collisions with the container or with each other are totally elastic. And number five, the average kinetic energy of the gas particles is proportional to the Kelvin temperature of the sample. So the kinetic energy is then directly proportional to the velocity of the gas. Okay, so the higher the kinetic energy, the higher the velocity of the gas. So the faster these gas particles move, the lower the kinetic energy, the slower the gas particles move. So since the kinetic energy is proportional to the temperature, we can say as the temperature increases, the kinetic energy increases and the velocity of the gas increases. As the temperature decreases, the kinetic energy decreases, and therefore also the velocity of the gas decreases. Okay? So this kinetic molecular theory also it was formed by pulling from all four of our underlying experiments, the Boyle's law, Charles' law, Avogadro's law, and Dalton's law, to sort of pull together into this five postulate KMT, kinetic molecular theory. So within this theory, so let's delve into a little bit with that postulate five again, talking about the kinetic energy associated with the temperature. Okay, and so again, that kinetic energy that we talked about, I told you was proportional to that velocity. And so here we have an equation: U is equal to the square root of 3RT over m. So I don't need you to memorize this equation specifically, but understand that velocity, as we mentioned previously, is dependent on the temperature, but it's also proportional or inversely proportional to large m here, which is the molar mass of the gas. So what that tells us is if we are at a constant temperature, if our T here is held constant, and we change the molar mass of the specific gas that we're talking about, we're going to affect the velocity inversely. So if we have an increasing molar mass of our gas, we're going to have a decreased average speed or average velocity there. Okay, so lighter molecules, so lighter weight molecules are going to move faster than our heavy molecules when you're dealing with constant temperature. Okay, so that is inherent to postulate number five as well. And so here we take a look at some data showing that the x-axis is the speed of gas of a collection of gas, and the y-axis is the percent of helium atoms. So we're dealing with all the same molecular weight gas and looking at the speed of that helium gas when you change the temperature of that gas solution. So we can see that at low temperatures, at 200 Kelvin, we can see that the large majority of our helium gas is moving at a slower speed. But as we increase our temperature from 200 Kelvin to 600 and then to 1000 Kelvin, we can see that we have a larger proportion of our gas that are moving at a much higher rate of speed. So that sort of shows our kinetic molecular theory, KMT theory, postulate five, that shows as we increase our temperature, we increase the speed of our material or speed of our gas movement. Okay, so based on this idea, I want you to pause for a second and rank the following gases by average speed traveled from slowest to fastest with Cl2, F2, Br2, O2, and CO2. So pause the video and work that out on your own. Okay, so we're going to rank these from slowest to fastest. So slow to fast, looking at these individual gases. And so we know that as we go from large molecular weight to small molecular weight, we go from slow to fast. So if we take a look at our periodic table, we can rank these in order of their molecular weight. Oh, so I spelled slow wrong, sorry. Slow to fast. Okay, so our largest molecular weight here is Br2, followed by CO2, which is then followed by Cl2, followed by F2, followed by O2 being the fastest. Okay, so we go from our largest molecular weight to our smallest molecular weight. Okay, next, at which temperature will nitrogen gas have the slowest average speed? 25 degrees Celsius, 253.15 Kelvin, negative 30 degrees Celsius, or 300 Kelvin. So pause the video and think about that for a second. Okay, so we want to take a look at each of these temperatures here and determine which one is going to be the lowest temperature. So we know that at low temperature, we're going to have low speed. At high temperature, we're going to have high speed. So in order for us to compare these temperatures here, we want to put them all in Kelvin so that we know we can compare them very easily to each other. So we know we go degrees Celsius plus 273.15 equals Kelvin. So our first one here, if we go 25 degrees Celsius plus 273.15 Kelvin, is going to give us 298.15 Kelvin. And when we have negative 30 degrees Celsius plus 273.15 Kelvin, will give us a final answer of 243.15 Kelvin. Okay? So we can take a look at all the numbers given to us here and see which one is going to be our lowest temperature to indicate which is going to give us the lowest speed. So we find that negative 30 degrees Celsius corresponds to 243.15 Kelvin, which is the lowest amount given to us. So negative 30 degrees Celsius is our correct answer. Okay, next we want to discuss the behavior of real gases that actually exist in the world as we know it. So if you recall, we previously presented data showing the molar volume of all gases is approximately 22.4 liters regardless of the identity. And I showed you all of these different individual gases that showed that all of their volumes of 1 mole of that gas are very close to that 22.4 liters. But you should have noticed that there was slight variation in the actual volume of each of these individual gases. So that raises the question, why do these values differ slightly based on the identity of the specific gas? Because we already told you that the ideal gas law, PV equals nRT, does not depend on the identity of the gas. So why do we have this subtle variation that has to do with the identity of the gas if ideal gas law doesn't involve it? The answer is the fact that real gases, the gases that actually exist on Earth, in real gases, molecules exhibit a slight attraction for each other when the pressure increases or volume decreases. Okay, so if we take a look at our equation here, PV equals nRT, this is called the ideal gas law equation. And the key word here is ideal. So ideal means in a dream scenario, this is what gases would behave like. We know in the real world, we are not in ideal conditions. We are in real conditions. So in ideal conditions, we know that molecules, gas molecules that are in a container do not interact with each other. But what we're seeing here is real gases, when we compress our volume down, these gas molecules can start to interact with each other. And so this interaction of this gas together has to be accounted for in a real gas equation. So this introduces the van der Waals equation, which is an adjusted gas law equation that accounts for these intermolecular interactions when we are increasing our pressure or decreasing our volume of our gas. So we can see that this equation sort of mimics our ideal gas law equation, where we have a pressure term and a volume term is equal to nRT. But what we can see here is that this pressure and volume are adjusted by a fudge factor. So the pressure is adjusted by A times n squared over V squared, where n is our number of moles and V is our volume, and A is a correction for intermolecular attractions. And this A term is specific to each individual type of gas. And our volume term is corrected by n times B, where n again is our number of moles, and B is another sort of fudge factor that corrects for molecular volume. And so this B term again is specific for each individual type of gas. So you won't have to memorize this equation, it would be given to you. But this equation would also be given to you with a table of these van der Waals constants here that give you our A term, either when you're dealing with pressure units in bar, or A term if you're dealing with pressure units of atmospheres, and then our B term. So so these A and B terms are indicated for each individual type of gas that you could work with. So if we take a look here at question 7, assume that you have 0.500 moles of N2 gas at a volume of 0.6 liters at 300 Kelvin. Calculate the pressure in atmospheres using both the ideal gas law equation and the van der Waals equation. So this will show us what actual difference do we observe by using the van der Waals equation compared to the ideal gas law equation. Okay, so let's take a look. So our ideal gas law equation, we know, is equal to PV equals to nRT. So we want to solve here for our pressure. So our pressure is going to be equal to nRT over V. So we have all those values given to us for the ideal condition. So we can just plug and chug. So we know our number of moles is 0.500 moles. Our gas constant is 0.082058 liters atmospheres over mole Kelvin. And our temperature we know, sorry we're running out of space here, is 300 Kelvin. Over our volume, which is 0.600 liters. So we can plug and chug here and say that our pressure in the ideal condition is equal to 20.5 atmospheres. Okay, so just for convenience, I'm going to write that up here in the upper right-hand corner. So our pressure for the ideal equation is equal to 20.5 atmospheres. So now let's solve this equation using our van der Waals equation, which accounts for real gases. So our van der Waals equation says that pressure plus our A times n squared over V squared times our volume minus n times B is equal to nRT. Okay, so we want to be able to solve for our pressure P. So to do that, we're first going to divide both sides. So sorry, that's equal to nRT. We're first going to divide both sides by V minus NB. So that's now going to say that P plus AN squared over V squared is equal to nRT over V minus NB. Now we can subtract AN squared over V squared from both sides. Okay, and that will now isolate and solve for our pressure. Okay, so now It's a simple plug and chug sort of problem. And so all the values that we have all the values given to us, the only values we have to look up is B and A. And so we go to the table given to us in the problem, and we take a look at that for that value for N2, and we find that our A term is going to be equal to 1.351, and our B term for N2 gas is be equal to 0.0387. So we can simply plug in all of our values. So our pressure is equal to our number of moles, 5.00 moles, times our gas constant, 0.082058 liters atmospheres over mole Kelvin, times our temperature, 300 Kelvin, over our volume, 0.600 liters, minus our number of moles, which is 0.500 moles, times our B term, which we stated is equal to 0.03875, and that has units of liters over mole. Minus our A term, which has a value of 1.351, and that has units of atmospheres, liters squared over moles squared, times our number of moles squared, so 0.5 moles squared, over our volume, 0.600 liters squared. So we simply plug all of this in our calculator, and we find our final pressure in the real condition is equal to 20.3 atmospheres. So if we compare the real pressure to our ideal pressure, we see that the difference is only 0.2 atmospheres. So it's really not that big of a difference between the two, but it's important when you're dealing with an industrial situation where you could have people's lives in jeopardy. When you deal with slight changes in pressure, dealing with an actual condition is really critical. All right, that's it for the day. Thank you.